Equilibrium analysis tells us where systems can rest, but political economies don't rest. They move, they evolve, they crash. To understand dynamics, we need simulation, actually running the model forward in time, watching how variables interact, seeing how small changes cascade into large consequences. This is where Saylor's mathematical framework becomes a laboratory. We can experiment with societies that don't exist yet, replay history with different parameters, and stress test political arrangements before they fail. Let's fire up the simulation. Simulation means solving differential equations numerically. We start with initial conditions, values for W, N, L, E, and P at time 0. Then we step forward in small increments, computing how much each variable changes. At each time step, we calculate all 5 derivatives using the current state. Then we update each variable by its derivative times the time step. Repeat. The result is a trajectory through 5-dimensional state space, the path the political economy takes over time. Different numerical methods exist. Euler's method is simplest, but can be unstable. Runge-Kutta methods are more accurate. For Saylor's model, we need methods that handle stiff equations, systems where some variables change much faster than others. The good news: modern software handles these details. We specify the equations and initial conditions. The computer traces the trajectory. The art lies in choosing meaningful scenarios and interpreting what the trajectories tell us. Let's establish a baseline, a middle-of-the-road political economy, not extremely unequal, not extremely egalitarian, moderate norms, functional institutions. We set initial conditions: W equals 0.4, moderately concentrated wealth; N equals 0.6, reasonably strong social norms; L equals 0.5, neutral legislative position; E equals 0.5, moderate executive power; P equals 1.0, normalized production capacity. We choose middle-range parameters: alpha, the wealth accumulation rate, at 0.1, beta, the norm regeneration rate, at 0.05, gamma, the legislative responsiveness, at 0.2, delta, the executive power generation, at 0.1, epsilon, the production growth rate, at 0.03, tau, the time delay parameter, at 5 years. Now we simulate. What happens? The system oscillates slightly, then settles into a stable equilibrium. W drifts up a bit, L compensates, N holds steady. This is the democratic equilibrium basin. The system absorbs small perturbations and returns to balance. This baseline tells us, with these parameters and initial conditions, democratic stability is possible. The feedback loops balance. No single force dominates. But what happens when we stress test this society? Scenario 1. Inequality shock. We take our baseline society at equilibrium and suddenly increase W from 0.4 to 0.6. Maybe a technological revolution concentrates wealth. Maybe a policy change favors capital over labor. The mechanism doesn't matter for the simulation. Only the new state does. What happens next? Immediately, conflict pressure rises. The gap between rich and poor widens. C increases. Higher conflict erodes norms. N begins falling. Trust declines. Institutions strain. Legislative pressure mounts. L shifts toward redistribution, but slowly. Gamma isn't high enough for instant response. Executive power faces demands for action. E may rise as the executive tries to manage the crisis. Production capacity, P, is affected by the conflict. Investment slows. Growth stutters. In our simulation, the system enters a period of turbulence. If the initial shock isn't too large, it eventually finds a new equilibrium. Higher W, lower N, more strained but still functional. But increase the shock further, and something different happens. The system spirals. N collapses. Conflict explodes. The democratic equilibrium disappears. The simulation shows us the threshold. How much inequality shock can this society absorb? The answer depends entirely on the parameters. Scenario 2. Institutional decay. Instead of a sudden shock, we model gradual parameter drift. We slowly decrease beta, the norm regeneration rate. Maybe trust in institutions erodes over decades. Maybe civic engagement declines. Maybe media fragmentation weakens shared narratives. This isn't a shock to state variables, it's a change to the system itself. In the simulation, the effect is subtle at first. The equilibrium shifts slightly. N drifts down. The system compensates. But as beta falls below a critical threshold, the simulation shows bifurcation. The democratic equilibrium becomes unstable. Small perturbations that previously damped out now amplify. Eventually, even a minor shock triggers catastrophic transition. The society that could absorb a 0.2 W shock when beta was healthy now collapses from a 0.05 shock. This scenario illuminates a crucial dynamic. Gradual erosion of parameters can make systems fragile without visible symptoms until crisis hits. The simulation lets us see the fragility developing to identify early warnings before collapse. Scenario 3. Policy intervention. Can we stabilize a troubled system through deliberate action? Let's test. We start with a society trending toward crisis. W is rising. N is falling. The trajectory heads toward autocratic equilibrium. Now, we intervene. We boost gamma, perhaps through electoral reform that makes legislation more responsive. We slow alpha through progressive taxation. We support beta through civic education and institutional investment. The simulation shows early intervention is cheap, late intervention is expensive. Catching the system far from bifurcation, small parameter adjustments redirect the trajectory. The society glides back toward democratic equilibrium. But intervening near the bifurcation point requires massive changes. The basin of attraction has shrunk. You need enormous policy shifts to overcome the system's momentum toward autocracy. And intervening after crossing the bifurcation? The simulation shows that the old equilibrium no longer exists. You can't return to where you were. You have to build something new. This is the brutal mathematics of political intervention. Timing matters more than magnitude. Can simulations match history? Let's try to reproduce a known transition. Consider a society that democratized, remained stable for decades, then collapsed into autocracy. We won't name it, because we want to focus on the pattern, not the particulars. We set parameters to match initial conditions at the democratic founding. Strong N from revolutionary solidarity. Moderate W high hopes reflected in gamma. The simulation tracks the historical trajectory surprisingly well. The democratic period, the gradual decline in N as revolutionary generation passes, the rising W as economic development proceeds unevenly. Then, the crisis. In both simulation and history, a shock triggers rapid unraveling. N collapses, E surges. The system crosses into autocratic basin. The match isn't perfect. History has accidents and personalities that no model captures. But the structural dynamics, the underlying forces, align. This validation gives us confidence. The model isn't just mathematical fantasy. It captures something real about how political economies evolve. Not all parameters matter equally. Sensitivity analysis tells us which ones drive outcomes. We run thousands of simulations, varying each parameter slightly and measuring how much the trajectory changes. For Saylor's model, several findings emerge. Gamma, legislative responsiveness, is crucial. Small changes in gamma dramatically affect whether democratic equilibria exist and how large their basins are. Beta, norm regeneration, determines long-term stability. Low beta makes all equilibria fragile. The interaction between alpha and gamma matters as much as either alone. High wealth accumulation can be offset by high legislative responsiveness, but only up to a point. Initial conditions matter enormously near bifurcations, but hardly at all far from them. Sensitivity analysis tells policymakers where to focus. Some interventions are high leverage, others barely move the needle. The model identifies which is which. Simulation transforms the model from abstract mathematics into a policy laboratory. We've seen how shocks propagate, how gradual decay creates fragility, how intervention timing matters more than magnitude, how historical patterns emerge from structural dynamics. But simulation has limits. It shows possible trajectories, not certain futures. Real societies face shocks we can't predict. Real parameters drift in ways we can't model. And real humans make choices that no equation captures. The value of simulation isn't prediction, it's understanding. We run scenarios not to know what will happen, but to understand what might happen and why. Next episode, we'll explore the model's limits. What does Saylor's framework capture? What does it miss? And where should future research extend it? Your simulation challenge. Pick a society you know well. Estimate its WNLEP. Guess its parameters. Now imagine a shock, an economic crisis, a political scandal, a war. Which way do you think the system moves? Toward stability or toward transition? You don't need software to think in simulations. The model is a mental tool as much as a mathematical one. Next time, model extensions and limitations.